The AI high-level course does a lot of interesting things with differential equations that the AA high-level does not. And I want to go through that today by solving a few questions from past exams. This first one that I want to do is very recent. It is from May 2025, but it shouldn't be the first thing that you do if you haven't studied differential equations really well yet, because this one is already a second order differential equation that uses the second derivative. So if you still need to do other things before this, I recommend that you start by watching this video. And I know it doesn't sound like it should be the first one because it says it's about Euler's method, but that's definitely the place to start if you only watch around 12 minutes of it, because that's where the introduction to differential equations is. And then after that, you can go on to learn how to solve certain differential equations by hand without the use of the calculator. And this other video was meant for AA high level, but you're also just going to watch around 10 or 11 minutes of it because the AA high level does learn more techniques for solving stuff by hand. What they don't do is second order differential equations, which is the first thing that I want to do right now. So this trick, this substitution that he is mentioning right here, is what you should always do with a second order differential equation, even if he doesn't say so. This particular question was helping you and reminding you that this is what you're supposed to do. There was no y in the original equation. You're just creating that variable and saying that it is the derivative of x. So when you do that, the derivative of y becomes the second derivative of x, which you can then plug into the original equation, and that's where this second one is coming from. So always do this with the second order, okay? Even if the question doesn't say so. And now we are in a different place, but it's also a place that doesn't belong in the AA course, only here in AI, which is that we have a differential equation that is first order. We're just using the first derivative of x and the first of y, but it does involve more than one variable. We have x and y. So the next thing that you are going to do is to write this system right here as a matrix. Let's do the second line first. The dy dt needs to be this row of the matrix multiplied by this column vector, and it's minus 3x minus 4y that we want to see as a result. So we're going to put the minus 3 and the minus 4 in the matrix so that when you multiply the row by the column, that's what you get, minus 3x minus 4y. And we're going to do the same thing to dx dt, but the equation in the system for dx dt is just y. So the multiplication here shouldn't have any x and just one y. That's the matrix, okay? 0, 1, negative 3, negative 4. So the way that you should look at it is if xy is the vector, then this other vector on the left side is the derivative of the vector v, and v prime is equal to the matrix m times v itself. If you compare that to a differential equation with just one variable, it would be this differential equation, which is very simple, and you know the answer to this differential equation. It's just an exponential function times a constant with the m from the equation in the exponent of the exponential. So this is also what you're going to expect your solutions to the system of two equations to look like. In part A of the question, he is asking for the general solution for x. He's not going to ask for y because y is just an intermediate variable that you put in there to solve the question. The actual variable of the equation was x, so that's what he's going to ask about. And you kind of want it to be the same thing. But here's the thing. Now we're not dealing with just one equation, but two equations. It's a system of equations. So we're not going to just have one exponential, but two exponentials. And I know they look the same, but it's going to be one constant and another constant, and one value in the exponent, another value in the other exponent. Okay, so they are two exponentials with different values in the exponent. That is the kind of thing that counts as general solution for x. So far, you haven't really done anything to the question, okay? It's worth 5 marks, and they are mostly going to come from figuring out the values of the constants and the values of the m's. So let's find the m's first. The m's are going to be the eigenvalues of the matrix M. The definition of eigenvalues are the values of lambda that make this determinant equal to 0. And you do have to calculate this determinant by hand. The calculator is not going to do that because it knows how to find the determinant of matrices, but only when all of the entries in the matrix are numbers. So it gives you the number that is the determinant. But that is not what's happening here. In here we have still a variable lambda, so what is going to come out here is an equation. This the calculator doesn't do. But it's not a difficult thing to do. You just take this diagonal and you subtract this diagonal. So this one was minus 3, minus 3 is going to be plus 3. And then you want this to be equal to 0 to find the values of lambda that are the eigenvalues. Let's solve the equation. And you have two values here, -1 and -3. Those are the numbers that you want to put in the exponents for the general solution of the equation. And this is already the answer to part A. He asked for the general solution. The word general means that we still don't know the values of the constants. If we knew those, it would not be general. It would be one specific solution. So when we come back to the question, this is what part BI is going to ask you to do, and it's going to be another 4 marks. Find an expression for x. And then in order to go from the general to the expression, what he's giving you are initial conditions. Initially, so that means for t equals 0, x equals 0, and the derivative is -1. These are the initial conditions, so now we're going to plug them into our general solution. The first one is giving us 0 equals c1 plus c2. And in order to plug in the second one, I'm going to have to first take the derivative of this. So here's the derivative, and now plugging t equals 0 in there, this is what we get. We have now another little system of two equations and two variables. This is linear. It's very easy to solve. These are the values of the constant. And then to fully answer what the question asked, he asked for an expression for x in terms of t. So we're just going to put those values of the constants into the same expression that we already had. This one's the answer to part BI. We have 9 marks so far, which is a nice number of marks to have. And we didn't really have to think about anything in this question. So this is a really good method for you to just know how to do, because this type of question will appear over and over again. It's always the same, only the numbers are going to change. And as you can see, it is a lot of marks. So you get a second order differential equation, you name a new variable y equals dx dt. Then you plug that into the second order equation to make that into a system of two first order equations, write it as a matrix, find the eigenvalues of the matrix, plug those into the exponents of exponentials, put two different constants in front of each one, and then plug in the initial conditions to find the values of the constants. But I don't think that was the end of the question. He says sketch x against t in the interval from 0 to 4. Okay, so that's just typing and copying onto paper what we find in a calculator screen. Here we go, that's the function, and from 0 to 4, you put this sketch into your exam. And now this is the first time where we're going to have to care about what the context was in the question. There is a report, and they're going to buy some shares of something and then sell them later. The context of the question was that the value of the share was the x. So it started here, went down for a little bit, and then went up again. Oh, actually, I'm being sloppy. It doesn't begin at 0, 0, 5. It begins at 0, right? That's what they told us. That's the initial condition that they gave us for the equation. And if you're finding it strange that the value of a stock is being negative numbers, I found that strange too, but I guess they just didn't care. That's what they gave us. It started at 0 and decreasing. So anyway, use your graph to find how long after the report is released. So they're asking for a value of t. The analyst should wait to buy the shares in order to maximize their profit. So she should buy when it's at its lowest point. What they're asking for here is the value of t of the local minimum. And then you just find that in your calculator. Now, the upper limit of the profit that she can make, she should sell at the highest point. Now, if you interpret the question as saying that this should only happen in the interval from 0 to 4, then you're supposed to take the value here and subtract from the value at 4. But I don't think that's what they meant. I think they meant for you to look at the asymptote. And in the long run, as we can see in this picture, the value of the stock is going to get back to 0. So the limit of the profit that she can make is when she buys here, sells at infinity. So it's the y coordinate of this local minimum, which makes sense, right? This was a C1 and a C2. One of them is asking for the horizontal coordinate and the other one is asking for the vertical. Now for the rest of the question, he changes his original equation. The right-hand side used to be 0, and now it's this complicated looking thing that depends on both x and t. But I'm not going to do part D right now because it is about Euler's method. So now is the time when I think if you don't know Euler's method, you should go back to this video and watch the rest of it to learn how to do Euler's method. It's not this exact question. I was working with other problems there, but it's the same thing. Here, question number 2 is giving us another system of differential equations, but this time it's just a system. He actually does have two variables in his context. It's the populations of two different things that he is observing. What I mean is that in the previous question, there really was only one variable, x, and the y was an auxiliary variable that we created as being the derivative of x. But this is not happening here. X is x and y is y. A lot of what we're going to do doesn't change. We wrote the system as a matrix, and now he is asking us to find the eigenvalues and the eigenvectors. I did use my calculator here, but just to solve this quadratic equation, because like I said, it doesn't do the determinant with the variable. So those are the eigenvalues. We already have 3 marks, but I haven't told you about the eigenvectors yet. So here's the thing. Each eigenvalue is going to have a corresponding eigenvector. So let's do the 0.2 first. The eigenvector associated with the eigenvalue 0.2 is going to be the vector that satisfies this equation here, where M is the matrix that we are working with. And I know if you've never looked at this before, it sounds very silly. Doesn't that just mean that M is equal to 0.2? Well, no, because this doesn't make any sense. M is not a number. M is a matrix. And also M is not the thing that we're trying to find. It's not a variable. It's a matrix. It acts like a number, but in 2 dimensions. We have 2 dimensions to work with here, x and y. So finding V is going to be about finding x and finding y. What this means about the definition of the eigenvector is that in the direction that we find this vector, say it's here, I'm drawing it in a random place because I haven't calculated yet. So if you take a point along this line and then you multiply the point by the matrix, what you're going to get as an answer is not a random point somewhere else, it's a point on the same line. In this case, it's going to be 0.2 times, so it has shrunk, but on the same line. And if the eigenvalue was bigger than 1, then it would be farther away than the original point, but also on the same line. So that's why eigenvectors are interesting. They are directions in this two-dimensional plane that we're working in, where applying the matrix doesn't really make a transformation that involves 2 dimensions. It's one-dimensional on this particular line. That is the eigenvector. And mechanically, it's just about solving the system of 2 equations. Here I have moved everything to the left and multiplied everybody by 10. And as you can see, I am reaching an indeterminate system because this equation and this equation are actually the same thing if you just multiply by -2 here. Finding an indeterminate system in general when you are solving a linear system for other reasons, it can be annoying when this happens, but specifically when you are looking for eigenvectors, this is always going to happen because we are not looking for a point xy, we are looking for a line. So we absolutely need a degree of freedom. We need an indeterminate system. And in this case, the eigenvector associated with lambda 1, 0.2 can be written as the vector 1, 1. It could be 5, 5 if you wanted. It can be anything as long as x minus y equals 0. But of course, I'm always going to pick the simplest number. And then you're just going to do the same thing again, but with 0.5 instead of 0.2. And again, the simplest numbers to pick here are 1 and -2. So that is the answer to part A2. We found the eigenvectors. It's this one and this one for the eigenvalues that we had already found before. Hence, write down the general solution of the system of equations. And this is analogous to what we were doing before. The general solution was this one, where we had already placed the eigenvalues in the exponents, but we hadn't yet found the values of the constants. So that's what we want to do now, but here it's different. He wants it for the system of equations, not just for x. This difference is happening because in the other question, it was a second order differential equation. So y was not a real variable, and here they both are. So he doesn't just want an expression for x of t, he's going to want a y of t as well. And the thing is that you can't write them separately. X of t is this and y of t is that. You have to write them as a vector x and t, because you are going to have a constant that you need to find at some point, but then the eigenvector comes here, multiplying the exponential with the eigenvalue in the exponent. And of course, you have to add a second term exactly like that for the second eigenvalue and eigenvector. This is the general solution that he asked for, okay? This is only 1 mark. He's just checking if you know this. This problem didn't give us an initial condition, at least not yet. I'm not sure if he's going to do it later. So we're not going to find the values of the constants C1 and C2 right now. Instead, he wants us to sketch something. He wants to sketch a phase portrait. Okay, but what is a phase portrait? Here is the thing. M and S are functions of time. I'm just drawing a random thing, okay? This is M and this is S. But this is not what he wants us to draw. Remember, we have 3 variables here the whole time. They are time, M, and S. But a phase portrait is not the graph of the functions M and S. The phase portrait is a graph that has M in one axis and S in the other axis. And where is time? Well, time is not here. Each time is going to give a point in the sketch. An interesting observation is that we can't draw this kind of sketch for any system of differential equations. It has to be a system of this kind right here, where notice that the right-hand side of the equations don't depend on t at all, because if, as well as depending on the current values of s and m, the derivative also depended on time, then being at this point at time 0 would maybe make this function, but maybe being at the same point on a different time would make a completely different trajectory. So you can't sketch because it depends on time. And he just wants it in the first quadrant, okay? This is because his variables are representing the populations of something, so it wouldn't make sense for them to be negative. Things that he wants on my sketch: the equation of the line defined by the eigenvector in the first quadrant. Which one is he talking about? We have 2 eigenvectors, but only one of them is in the first quadrant. So this line that he wants, the equation of the line is just y equals x. And then he also wants us to show at least 2 trajectories either side of the line. So 4, okay? 2 over here and 2 over there. Using arrows on the trajectories to represent the change in population as t increases. So he's being very explicit about what kind of picture he wants to see. I am going to ignore the restriction about the quadrant for now, because I want to show you in general what this kind of picture looks like. So here is the first eigenvector, the line that he wanted, but I'm also going to put the other line in the picture. So that one is y equals -2x. They're not perpendicular, okay? Be careful here. They could be, of course, but they don't have to be. That's what I'm saying. And here's the thing. I told you that both eigenvectors are lines along which the system evolves in one dimension. It doesn't leave the line. So what we have to do is put some arrows here. Is it going that way or is it going this way? So in other words, is it getting bigger or is it getting smaller? So listen, this eigenvalue is being used in the exponent of an exponential for the function of x with respect to time. So this is a thing that grows over time, okay? It's an exponential and time is moving to the right, so the function is going up. By up, I mean that it's getting bigger, but in the two-dimensional picture, bigger means away from the origin. So if we were to consider the other side, it would point that way. The only way for these arrows to be pointing inside is if the eigenvalues were negative, because then we will be talking about an exponential that has been reflected horizontally. So as time gets bigger, the value of the function is getting smaller. So in some equations, it can happen that one of them is positive and the other one is negative, but in this case, both are positive, 0, 2, and 0, 5. So it goes like this. So these two are very special trajectories because they are along the directions of the eigenvectors, but we also have to draw more than this, like trajectories that start at other points outside of these lines. And I think it's easier to begin explaining this in a different case where one of the eigenvalues would be positive, like the ones we had, but the other one would be negative. In this case, we still have the arrows pointing out along the eigenvector of the positive eigenvalue, but along the other eigenvector, we are going to have arrows pointing in. And everywhere else, we're supposed to have things that sort of follow the same general direction. So this point here is not on the eigenvector, but it is close to it, so it's going to do something similar. As we get closer and closer to the other eigenvector, then that starts having more of an effect and the trajectory goes this way. So everybody over here would be doing something like this. And in this other quadrant, it would be doing this. We start by following this one, and then we gradually turn around and follow more in the direction of the other eigenvector. So the complete picture would look something like this for this case. Now, when we have two positive ones, it can be a little bit more complicated because if they were both positive but equal to the same number, then there isn't much of a mystery, right? All of the trajectories are just straight lines pointing outside from the origin. But if they were both positive but different numbers, like is our case in the question that we're solving, then all directions are going to be pointing out, but one of them is stronger than the other. So as we leave from the origin, there's going to be two possibilities. Either we start by going more in the direction of this one and then gradually turn around to the direction of the other one, and this is going to be going on in all of the quadrants of the picture. Or it's going to be the other way around. We're going to start by going out through this direction and then gradually turn around and become parallel to this direction. And I would try to avoid memorizing which is which because this is the sort of confusing thing that you can memorize wrong. Instead, I like to think of what's going to happen in the long run when t is very large. Because the y equals x line is associated with the zero point 0.2 eigenvalue, and the other line is with the eigenvalue 0.5. So in the long run, this one wins, the bigger eigenvalue. The bigger eigenvalue pushes points more strongly than the smaller one in the direction of its own eigenvector. So in the long run, the directions are going to end up being parallel to this line, which means that they had to start from the other line. So this is kind of the picture that the exercise is asking us to draw. Trajectories with arrows pointing the direction, at least two on either side, right? So I'm doing more than two. This is what the phase portrait looks like. Another way that you can think about this is that if instead of two different positive eigenvalues, you had one positive and one zero, then in the direction of the eigenvector of zero, the trajectories wouldn't move at all. So everybody would be just parallel to the direction of the positive eigenvalue. And of course, they would be going out in that direction. Now, if you change that zero eigenvalue a little bit to become slightly positive, but still smaller than the two that we have in the other line, then there would be motion in the trajectories in that direction. It would everything be going out of the origin. But as you go from 0 to like 0.1, the picture can't change a lot suddenly. So it needs to look similar to this, which means that it's this direction that is going to bend first. So in the case of two positive eigenvalues, the trajectories start out parallel to the smaller one and then bend in the direction of the bigger one. You can also use this to think about the two different negative eigenvalues case. Again, if one of them was 0, nothing would be moving in that direction, so everybody would be parallel to the other one. But in this case, it's negative, so the trajectories are going in. Now, if you change that 0 to something that is slightly negative, like negative 0.1, now everybody wants to go in, but the picture can't change a lot. It still has to have these sort of parallel lines. So the change is going to happen just here. Everything's going to start out parallel to the negative 2 and then bend in the direction of the negative 0.1, which is the smaller negative eigenvalue, like the less negative. And that's how we should decide in this case which direction goes first. And that's why I said that this case was easier with one positive and one negative, because then you don't have to think about these things. But now that we have done our first quadrant picture, like the question asked, let's go ahead and see what else it wants, like parts D and E. We're not done with this question yet. So now he's sort of giving me some kind of initial condition. When t equals 0, x has a population of 2,000. That doesn't really tell us where we are in the picture, because 2,000 can be anywhere here. So it might be down here under the eigenvector, or it might be up there. We don't know. And that's exactly what he wants us to think about, because write down a condition on the size of the initial population of y, which is going to tell us whether we are down here or up there, if it is to avoid its population reducing to 0. Now, I find this phrasing confusing. Who is its? Is it y? Assuming that that's what we're looking for, we want the population of y to not reach 0. If it was down here, then eventually the population of y does reach 0, because it goes down this way. The condition that he wants us to write is that y needs to be up here. So above 2,000. This point right here is the point 2,000, 2,000, right? It's a point on the y equals x line. It is known that y has an initial population of 2,900, and we are still using x as 2,000. So I don't know, we are kind of here. This is the sort of trajectory that is eventually going to make not y, but x be equal to 0 at some point. This point here has coordinates 0 something. So that is what he is asking us about. Find the value of t at which x is equal to 0. And this one has a lot of marks, because now we have to calculate things. We are going to need a specific solution, an equation to plug numbers into and find the value of t that he's asking for. So this is the general solution that we found earlier, and these are the initial conditions that we are now working with. We're going to plug them both into the general solution, but at the same time, okay, because this is a vector equation. It has x and y. We're not going to plug them in one by one like we did in the second order equation example. Here, all the exponentials have become 1 because t was 0, the exponent was 0, and the constants have been multiplied inside of the vectors, okay? This, again, is a system of two linear equations. You solve it and find the values of the constants. Now you're going to plug these constants into the equation, and we want to find out when x is 0. That was the question that he was asking. So you have a 0 here is equal to 2,300 times 1 times this, minus 300 times 1 times this. And then that just becomes an equation, and you use your calculator to find the value of t. So you see, the calculator used in this kind of topic is a lot more in the simple things like finding equations. It's not specific calculator commands that you need to learn in order to handle differential equations. When it comes to actually the math, you have to do it by hand. It's just the calculations that the calculator is doing for you. And this last request is going to be very easy. Find the population of y at this value of t. So for that, you just use the second line of your equation, y equals 2,300 times 1 times e to the power of this with the t being this value, and so on. And then that's going to be a number. That's the value of y that you're looking for. Okay, question number 3 is a paper 1, so he wants to be a short question. He is not going to ask you to do all of these steps that we've been talking about. So he just gives you the system. He already gives you the eigenvalues and the eigenvectors. You don't have to do that part. It's just going to be interpreting the meaning of these numbers. He's not testing whether you know how to find them right now. There's also some initial conditions right here. Find the value of dy dx when t equals 0. Here's the thing. He gave us dy dt and dx dt. So what you should do right here, it looks kind of like this, right? If the dt's would cancel out, then this is dy dx. So instead of multiplying by dt dx, which is a weird thing, what you actually have is dx dt. So you're going to divide by that. When t equals 0, which means initially, we have x is 8 and y is 10. So let's take the 8 and the 10 and plug them in here. So now we have the values that we need. dy dt is -4 and dx dt is 4. So the thing that he was asking for is just -1. On the following axis, sketch a possible trajectory for the growth of the two fungi. So now we're going to start by putting the eigenvectors in our picture, just like we did in the previous examples. The eigenvectors are 2, 1, and 1, 2, so they're both in the first quadrant this time. This is relevant because, again, these are populations, right? So, again, he wants the first quadrant because populations can't be negative. This one is the line y equals 2x. This one is the line y equals x over 2. Now let's see which one goes with each eigenvalue. Okay, the second one is y equals 2x because 2 is equal to 2 times 1. So the top line has the eigenvalue -1. The other one is 2. These lines extend to the other quadrants. This line has arrows pointing in, and the other line has arrows pointing out. So we know what to do with the trajectories in between them. They start by going this way, eventually turn around and go that way. These are the arrows. Down here, it's this way, and up there is going to the left. Now let's see what the question was. Sketch a possible trajectory, so just one. Okay, so we need to think about the initial condition to decide between these possibilities, okay? It's x equals 8 and y equals 10. So when x is 8, this line is at 4, and the other line is at 16. 8 is around here. So the part of the picture that we're talking about is the one in between the two eigenvectors. There is no scale in this picture, so I don't have to put the 8 that far away. I can just say that the trajectory that I am talking about is this one. I think that he doesn't want me to sketch the trajectory going to infinity and also to -infinity in the time, okay? I think he wants me to start at t equals 0. That is why he told me that the dy dx is -1 at t equals 0. So let's just find a point in the trajectory where that can be true. And I think it's here, right? Dy dx does look like -1 here. The tangent line is kind of this blue one. So I am not going to use this side of the trajectory. And he said to make clear any asymptotic behavior. I don't know exactly how he expects me to make that clear in the picture, but this is the asymptotic behavior. It is getting close to this line. Okay, so now before we move on to the next question, I want to mention that there are more cases that can happen in how does the phase portrait look like. And it all depends on the numbers that the eigenvalues turn out to be when you calculate the determinant. I've shown you a couple of possibilities so far. We have one positive and one negative does this. Two different positive eigenvalues are the blue and the green portraits in this picture. But I do need to say more about the two equal eigenvalues, okay? Because this case does not always look like the pink portrait in this picture. And this one was two different negative ones, which is the same as two different positive ones. But the thing is that when we have two eigenvalues that are the same, we don't always get two eigenvectors like I may have led you to believe in the previous picture. So for example, say that this is the matrix, right? And now I want to do this minus the identity matrix to calculate the determinant that gives me the eigenvalues. This determinant is going to have to be equal to 0. Well, clearly I'm getting lambda equals 2 with multiplicity 2. But let's look at the eigenvectors now. So this is mv equals lambda v. The system that this makes, the first line is 2x plus y equals 2x, which is giving us y equals 0. And there is not much that the second line can do. The second line is just 2y equals 2y. So the only eigenvector that we are finding is the one where y equals 0. Then you can put any number for x because the equations of the system didn't give any restrictions on that. So 1, 0, right? It is an easy eigenvector to sketch. It is the horizontal axis. And along that direction, the eigenvalue is 2. So it's positive, it's going outside. That doesn't really tell me anything about the rest of the picture. So what you're going to do in this situation is, let's write down the differential equation where this matrix came from. And now we're just going to choose a different point to look at, a point that we don't know anything about yet. Please pick the easiest one. This is the point 0, 1. And then let's just plug that into the system and see what happens. So we have both the x prime and the y prime being positive, so both coordinates are increasing, but the y coordinate is increasing faster. So at that point, we have a trajectory that points this way. And the way to connect the dots between the blue and the pink in order to make this into a phase portrait is that this thing came from here. It starts by going outside from the origin in the direction of the eigenvector, but then it turns around and comes back again, eventually becoming parallel to the eigenvector again, but somewhere else. This looks kind of bad. Let me try to make a better picture. And all of the other trajectories are going to do something similar. They're going to start coming this way, they're going to turn around, and then they're going to eventually go the other way. And the same thing happens on the other side, except kind of backwards, but always going outside. And I want to give you a little bit of an explanation of why this picture looks like this, because it's just so different from the other one that you can get with the same eigenvalues. Okay, this pink one is eigenvalue 2 with multiplicity 2. And this one is also the same thing, but the difference is in the eigenvectors. This one has two different eigenvectors, and this one does not. So this is not the correct thing to be comparing it to. We should compare it more to this one, which has two different eigenvalues, and then we can think about what happens when they get closer together. One of them is gradually changing until they both become the same eigenvalue with multiplicity 2. So the example here is this matrix, which has one of the eigenvalues is always 2, with the eigenvector pointing this way. Well, both ways, right? To the right and to the left, going outside because 2 is a positive number. And the other eigenvalue of this matrix is 2 plus a, which is giving us this other eigenvector here. The eigenvector is 1a, and the other one was just 1, 0, the horizontal vector. But as we make this a get closer and closer to 0, which is what I plan to do with the slider here, that a is going to go to 0, then this a is also going to go to 0. So the two eigenvectors will become the same. That's why we didn't have two different eigenvectors in that case. We're only looking at one trajectory here, which is this red one, but I think that's enough to understand. Look at what it's doing. It starts at the origin, going to the left, which is following the direction of the eigenvector. And then it turns around and bends in the direction of the other eigenvector. They don't really look parallel now, because I said here that this kind of thing eventually makes them parallel, but that's just because we're not looking far enough. If we zoom out here, we will see that eventually they get more and more parallel. Maybe you need to zoom out a long way. So for the purposes of the video, it's not good if I do this much. Let's just believe that they are going to be parallel. And with this amount of zoom, you can't even see the beginning of the trajectory, how it was actually following in the direction of the horizontal eigenvector, right? You can't see that from this distance. But look what happens when I make A smaller. See, the eigenvector is going down. It's getting closer to the horizontal. Its slope is becoming smaller because the slope was A. And you can also see the initial part of the trajectory more and more. I can even zoom out more here so that you see that it's still eventually going to be parallel to the second eigenvector. But the thing is that as A goes to 0, this is becoming bigger and bigger, right? It takes more time to happen, but it does happen. And when it gets parallel to the second eigenvector and A keeps getting smaller, then it's just getting parallel to the same eigenvector again, which is what we were drawing here. You can imagine that originally there used to be a second vector here, parallel to which these lines wanted to be, but this just became the same line, horizontal. I really like drawing this one. I don't like writing the solution so much. It's annoying. Let me show you how to do that. Because you only found one eigenvector. And in order to write down the general solution, you need two eigenvectors. So what you're going to do is that you're going to solve the system again, but this time we are adding the eigenvector to the right side of the equation. Of course, the thing that we find is no longer going to be an eigenvector because that's not the system. But it is a vector. So the first line is telling me that y needs to be 1. The second line is not telling me anything. So now I can choose the first coordinate of this vector w, and I'm just going to choose 0 again because it's the easiest number that I can choose. So with these two vectors now, I am going to write down my general solution, but it's not going to be exactly how you think it's going to be. This would be the thing that we initially expect, right? Two constants with two vectors and the same eigenvalue. But that is not exactly right. That is a missing term. We need to put the first term again here, and this time multiplied by t. So this gives a slightly different shape to the solution. It's not just an exponential anymore, but it's an exponential times t. And this particular example gives simpler looking expressions because of the zeros in the eigenvectors, because some of the terms disappear. Now, I haven't really seen this happen in IB exam questions, okay? It's not clear to me whether they would require you to know how to do this, the general solution in this weird case. But I did see one of these solutions appearing in a paper 3, which is where they allow themselves to put things that are not exactly part of the syllabus, right? So in this question, the matrix was 3, 1, minus 1, and 1. So if you look for eigenvalues of that, you only find one of them, exactly as in the example that we were just looking at. And the eigenvector is going to be 1 and minus 1, right? I'm not going to waste time calculating because he's just asking to verify. And then here's the thing, in the next item, letter C, he also asks to verify, but this vector here is the eigenvector 1 and minus 1 times t, plus another thing that is just a vector 0, 1. He is not asking you to know where the 0, 1 came from. He's just asking you to verify. But where it came from was solving the system with the eigenvector added to the right side, like I was telling you. This is the system that you need to solve. This is what it simplifies to. And it's, again, an indeterminate system. And the simplest way to solve the system is to just say that x is 0 and y is 1, which is exactly the one that he chose. So that's the case that I think is the most complicated one, but we still haven't covered all of the cases because when you get a 2 by 2 matrix and you find the eigenvalues, there's also the possibility that the eigenvalues are complex numbers. So in case of complex numbers that have no real parts, the trajectories are just going to be going around in circles around the origin. Sometimes they're going to be turning clockwise, sometimes they're going to be turning counterclockwise. And the easiest way to decide which one it is to just calculate at one specific point and see if at that point you're going up or down. Everything else needs to be following the same pattern. This is similar to what we did here to figure out the direction of this trajectory. Now, if the complex number has a real part and this real part is positive, then instead of just circling around and around, it's going to sort of spiral out, which makes sense, right? Because a positive eigenvalue wants to make things move away from the origin. And it could spiral out in two different directions. This is also positive real part. And again, to figure out which is which, just pick a point and see if it's going one way or the other way. If the real part was less than zero, then it's the same kind of trajectories, but they're just moving inside of moving out. So for linear systems, which is everything that we've been looking at today, which are the ones that can be written as a matrix, right? So the system of equations that they come from is always this system. The only thing that changes is the values of A, B, C, D. We have all of these interesting possibilities of things that can happen to how the trajectories look, but always around the origin. Interesting things never happen in other places. In order to have these interesting pictures happening in other points, you would need a nonlinear system. And it's a thing that I find very interesting to do, connecting the dots when you have more than one point with interesting things happening. So, for example, if this one is the one that everybody goes out, but that other point there has everybody going in, how can we connect the dots? What can the whole trajectory kind of looks like? Well, you can have one that starts here and goes directly there, but maybe this one needs to go out a little bit before coming back. This one needs to take a longer time to get there. And what about this one that's pointing completely the wrong direction? It's going to have to take an even longer path. So it's a very interesting exercise to put these things together and try to connect the dots, because it's not always possible. Like if this one wants everybody going outside and this one wants to go around in circles, then okay, you could leave from here and go that way, but now what? Now you are going to crash into this other one that came from there. So this is not possible. Some configurations work and some don't. If this one is going around this way, then maybe that one is the one that has one negative eigenvalue and one positive eigenvalue. Then in between here, the things are doing this, this, and this. But over here, this one does this, which matches perfectly with what the other one is doing farther away. But in any case, this is something that is very interesting, very pretty, but can only happen in nonlinear systems. This is from a paper 3 question, by the way, and then ask you to do other types of things. For example, they can easily ask you for an Euler's method, because being linear or nonlinear doesn't change anything in Euler's method. But I want to see if we can do something else with this question. So it begins when they tell you that an equilibrium point is a set of values for the two variables, which in this case are m and s instead of x and y, such that both the derivatives are zero. So let's work with this definition and figure out what the equilibrium points are for this system. But we're going to want this to be equal to zero and this to be equal to zero. One obvious solution is that both m and s are equal to zero, right? This is the point at the origin, the same as in the linear systems. But there must be something else going on here. Here I factored out the m from the first equation, factored out the s from the second equation, and now I see that m equals s equals zero is the solution where m is zero and s is zero, but that's not the only one. I can also have this thing being equal to zero. But then if that happens, s is not zero. So this one is not zero, but this one has to be zero so that both lines are equal to zero. So m has this value, s has that value. This was actually what the question was asking us to do, show that at the equilibrium point, the m is delta over gamma. And then find the value of the sharp population, which is the s, at the equilibrium point. Well, that's the alpha over beta that we've already found. So you got 5 marks here, and then the paper 3 question went on to do other things, such as ask you to do Euler's method. But that's not what I want to do with this question. I want to do things that he did not ask me to do, just to see if I would be able to do it in this example. So I've switched the names of the letters from MS to XY because I'm more used to that. And now I'm going to choose some values for alpha, beta, gamma, and delta so that we have numbers. So now the point 2, 3 is my equilibrium point, and also the point 0, 0 is an equilibrium point. Remember that these are the points where both derivatives are 0. So in other words, if your trajectory were to start at an equilibrium point, it wouldn't go anywhere because the derivative is 0. That's why it's called equilibrium. But now I want to draw the trajectories, and I know where my equilibrium points are. This is 0, 0, and this is 2, 3. But in order to figure out what the picture looks like, I need the eigenvalues and eigenvectors of a matrix that I don't have because this is not a linear system. So that's the catch. What's the matrix? How are we going to find these eigenvalues and eigenvectors of what? So let's do it with 0, 0 first. And the matrix that we are going to use, we're going to come from these two functions here. They are both functions of two variables, x and y. Let's call them f and g. And now we're going to put a bunch of derivatives in this matrix. This one is going to be df dx, df dy, and the same thing for g on the second line, okay? So df dx is 3 minus y, where you're treating x as the variable for this derivative and y is a constant. And when x is a constant, then this one is just minus x because y was the variable. The derivative of this term is 0 because x is a constant. Now we do the same thing for the second line. And this is the matrix whose eigenvalues and eigenvectors we want to look at. But the values of x and y in the matrix are going to be different for both of the equilibrium points. Let's do the 0, 0 first. By just plugging in x equals 0, y equals 0, we get the matrix 3, 0, 0, and negative 2, which is a very easy matrix. The eigenvalues are 3 and negative 2. The eigenvector of 3 is just 1, 0, so you get things going out over here. And the eigenvector of negative 2 is 0, 1, so you get these ones going in. Already on the left side, I am going to be able to connect the trajectories because there is no other equilibrium point over there. I guess down here as well. The only quadrant that I'm not going to do anything to yet is the first quadrant because first I want to check what happens to that other equilibrium point, 2, 3. So when I plug in those values, y is 3, so this is 0, x is 2, so here we have a negative 2, again a 3 here, and a 0 here. This is probably going to give me complex eigenvalues, but let's check. Yes, that's exactly what happened, and I'm getting eigenvalues with the real part equal to 0, which should be the type that just goes around in closed circles. But it's going to be going this way. It can't be going around the other way because it needs to connect to the other trajectories that are happening down here at the other equilibrium point. So yeah, that was a nice example, a nice question. Here is another paper 3 from a different year, also has a system that is nonlinear. He starts by just giving us a point and then asking us for the rate of change of both the x and the y. The geese is x and the foxes is y, he said so before. So here we just want to plug in numbers into dx dt. dx dt for 5, 5 is 10 minus 25 over 2, which is negative 2.5, and dy dt is 10. And then he goes on to say there are two equilibrium points, one of which is 0, 0 as usual. The other one is PQ. He is clearly going to ask you what P and Q are. But this year he did not give you the definition of equilibrium point. The previous question that we were looking at did say that, but this one doesn't. So clearly something that you need to know. An equilibrium point is when the derivatives are equal to 0. We're going to solve it in the exact same way as we did the other one. I'm going to factor out an x from the first line and a y from the second line. And that's giving me 3, 4. So those are the values of P and Q, 3 and 4. Hence, sketch a complete set of trajectories. This is exactly the thing that we were just doing, clearly indicating both equilibrium points. Okay, so we have the 0, 0 and the 3, 4. But in order to do the trajectories, we are going to need the matrix for both points. So this is F, this is G. The matrix is made up of the derivatives. This is df dx. And these are the derivatives of g. Now let's do it for both points. For 0, 0, I am getting the matrix 2, 0, 0, negative 3. This is extremely similar to the previous question. 1, 0 is an eigenvector going out with a positive eigenvalue of 2. The other one is negative 3 going this way. And the matrix for 3, 4 is this one, which is again going to give you complex eigenvalues with 0 real part, and they can only be rotating this way so as to match the directions of the rest of the trajectories. Oh, he did say complete, right? So let's include trajectories down here as well. Unless he talked about the domain, because I think these were populations of something. Populations can't be negative. So maybe he doesn't want me to sketch the other quadrants. I don't know. But there you go. This is one of the most interesting things in the whole of the AIHL syllabus, in my opinion. The last question here was just asking about the initial conditions that we had, which was 5, 5. Remember that at 5, 5, we had this derivative going to the left and up, a lot more up than to the left. So 5, 5 is around here to the right of 3 and above 4. And yeah, that looks pretty much like what I drew here. Question is, at this initial conditions, he is worried and assumes that the geese will quickly die out. The geese was Y, right? No, the geese was X. Suggest whether this assumption is supported by the model. I don't think so, because the X is going to the left, but it is going to go back up again at some point. This is a thing that goes around and round. So that's what you were supposed to say in this question. The population of geese is currently decreasing, but it is not going to decrease forever because it is in a trajectory that goes around.